Hello and welcome to this lecture. We've been so far looking at multiple random variables, in particular two random variables, how to define something called the joint PMF of two random variables, and then we looked at marginal PMF and conditional PMF. We went in that sequence, joint to marginal to conditional, but quite often in practice it will go the other way. So, the marginal PMF and the conditional PMF are much easier to define in practice, and then you combine that and make the joint PMF. So, it can go that way also, and so I thought I will show you a few questions where something like that happens. The marginal and the conditional are more naturally specified, and using that you go to the joint PMF. So, in fact the basic property that we have is this this factorization rule here, right. So, this rule is very powerful. Let me just make my go a little bit bigger. So, this is the basic rule, right. So, this says the joint PMF at t comma t prime is the marginal times the conditional, right. So, the marginal of x at t multiplied by the conditional of y given x equals t. So, this rule is quite powerful, and one uses that in very different ways to create the joint PMF. So, let us look at a few problems that it is easier to think in terms of problems here. Okay. So, here is the situation. Somebody is throwing a die, you get a number between 1 and 6, and then depending on what you get, you toss coins. So, supposing you get the number 2, then you toss a coin twice, okay, and toss a coin as many times as the number shown on the die, okay, and x is the number shown on the die, that is the one random variable you define, and y is the number of heads that you get after the coin toss, okay. So, the question asks what is the joint PMF of x and y, okay. So, here again the marginal of x is easy to define. X is uniform from 1 to 6, okay. Maybe this thing is a bit too big. So, x is uniform, and then what is given to you, notice, is y is the number of heads, but it is better to write down y given x equals t, okay. So, this random variable, the conditional random variable y given x equals t. So, you have thrown a die and x has taken a value t, as in the number t showed up in the die. So, you are going to toss the coin t times, okay, and y is the number of heads. So, y given x equals t is going to become binomial. We have seen this before, it is a Bernoulli event, right, a binomial of t comma half, okay, right, number of heads when you toss the coin t times. This is y given x equals t, okay. So, you have the marginal x and then the conditional y, and now you can use the multiplication to do. So, what does this mean? So, this is fx of t equals 1 by 6 for t between 1 and 6, right. What is binomial? F y given x equals t of t prime is t choose t prime, right, 1 by 2 to the power, okay. So, maybe I should write t choose t prime in a different way. I have been writing it like this, t choose t prime 1 by 2 to the power t prime times 1 by 2 to the power t minus t prime, but this 1 by 2 you can easily add here. So, you will get t choose t prime times 1 by 2 to the power t, right. So, t prime and t minus t prime you can add, you will get just t. So, this is t choose t prime 1/2 to the power t, okay. Fx of t is this, fy given x equals t is this. So, now one can do the factoring of fxy, right. So, fxy of t comma t prime equals fx of t times fy given x equals t of t prime, and notice t prime will go between what, t prime equals 0, 1, 2, so on till t, okay. So, that is the value here. So, if you plug it in, you will get 1 by 6 times t choose t prime 1/2 power t. So, this is the joint distribution, and if you want to make a table, let us make a table here. T would go from, let us make a table, maybe at least a partial table, okay. T goes from 1 2, 3, 4, 5, 6. And what will T prime go to? T prime is the number of heads that throws up in the one toss. It will just be, it will go all the way from 0, 1, 2, 3, etc. I'm only doing it partially. I put a dot 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 here. I'm not doing it fully. So if T became 1 and you toss the coin only once, the probability of getting heads is half, right? So it's very easy to write down. So this would be 1 by 6 times 1 by 2. Okay. Is that all right? So t is equal to 1, and then 1 choose 0 is just 1. Same way here, 1 by 6 times 1 by 2, and after that you will get 0. So maybe I should just write this down a little bit below. Okay, 1, 2, 3, then dot dot dot. So 1 by 6, after that it's all 0 here, right? What about for 2? For 2 here you will get 1 by 6 par 1 by 2 squared. Okay, so here you will get 1 by 6 times 2 times 1 by 2 squared, and here you will get 1 by 6 times 1 by 2 squared, right? So you can see how I'm just using this formula for different values of T prime and getting it done. After that 0, and then 3 you will have all 4 writing down, 4 you will have everything written down, and then 6 you will have everything written down. So it will have some sort of a upper triangular sort of shape if you write it down. So it's an exercise to fill this table for you. Go ahead and fill it out fully. So this is the formula. Okay, this is the formula. You just apply this. T is here, T prime is here. You just plug it in. You will get the value for each point. And remember, T prime goes only from 0 to T. Okay, so this is interesting, right? So for instance, the range of y given x equals t is actually 0 to t, isn't it? So it's a bit different depending on t. The range changes and the conditional distribution also changes. So this is a way in which conditionals and marginals are specified in problems. So most often when you look at a problem in a probability space, you always want to look for the marginal and the conditional and make the joint using that. It's much easier to work that way rather than think of the overall joint PMF. Okay, so hopefully this example showed you that. Okay, so we'll see a few more examples of this nature just to drive home the point. So this one is a little bit more complicated, as in I'm going to use Poisson distribution. If you remember the Poisson distribution, I'm saying here n is Poisson. So n takes values from 0 to infinity, and fn of k is e power minus lambda times lambda power k by k factorial, right? So this is for k equals 0, 1, 2, so on, keeps on going. Okay. Now given that n equals n, okay, so small n is being used here, so maybe I should use small n here. Let me use small n. Anything is okay, but let's use consistently what is given in the problem. So given the capital N is n, as in you sampled the Poisson process and you got a Poisson random variable. Given that Poisson random variable n took a value small n, you toss a coin n times. So previously you just threw a die, it was just 1 to 6 and saw the number that you got, and then you toss the coin that many times. Now I'm not throwing a die, somebody is giving me a Poisson distributed random variable. Okay, it may not be as easy as throwing a die to generate a Poisson random variable, but let's say maybe in your Colab or Python module you can see how you can generate a Poisson random variable. So you generate a Poisson random variable of with parameter lambda. Somebody does that and gives you a value small n, and then what do? You pick up a coin and toss it n times, right? Now you denote the number of heads obtained by x, and the question that is asked is what is the distribution of x? Okay, so notice what we can do here. So n, distribution of n is very easy. What is also easy is x given n equals n. Okay, so this is what's given to you. Given that the Poisson random variable took a value small n, what is x? X is you toss the coin n times, a fair coin, and counted the number of heads. What is that going to be? That is going to be binomial n comma half, isn't it? Right? So I know how that can be written down. Fx given n equals n of let's say k is n choose k half power k, isn't it? Okay, so of half power k, half power k times half power n minus k, that is just half power n. Okay, So, if you want, you can write it down fully. It's half power k times half power n minus k. I can add it all up and write it as half power n. Okay. So, and this k will go from 0 to n. Okay. This is what it is. All right. So, now I have the marginal of n, I have the conditional of x given n, I can find the joint distribution. Okay. What I am asked is actually the distribution of x. Okay. So, what is being asked is fx. Okay. But the way to go there is through the joint PMF. Okay. So, let us find the joint PMF. The joint PMF of f n x of n comma k, okay, this is equal to, this is the product of these two, right. So, e power minus lambda, lambda power n by n factorial times n choose k times half power n. Is that okay? And then n would go from 0, 1, 2, so on, and given n, k will go from 0, 1 to n. Okay. So, this is how this will look. I mean, it's very similar to the previous problem, right, except that the previous one ended at 6. Maybe you're happy with 1 to 6, but it doesn't matter where you end, you know, you just keep on going and you'll get that big binomial here. And this looks like a pretty complicated little distribution. It is a little bit, but let's see if we can make some sense out of it, right. So, now the next problem here is to find fx. Okay. So, how do you find fx of k from the joint PMF? You have to find the marginal from the joint distribution. The joint PMF is given, you have to find the marginal. How do you do that? You add up over what you do not want, isn't it? You do not want n, so you add up over all possible values of n. So, if I want fx of k, which is the marginal, this is going to be sum over n from 0 to infinity fnx of n comma k, isn't it? I add up over everything that I do not want. Okay. So, in this case, it is sort of difficult to put it into a table, because maybe you can, you know, I mean, you can just put n there and then write a table, but the table does not really help you that much. You can just work with these expressions. Okay. So, this is what you are going to add over n okay. Okay, you get e power minus lambda, lambda power n by n factorial times n choose k. So, remember there is this issue here. Okay, let me just come to that after writing it down. So, you will see here. So, k goes from 0 to n and n keeps going. Okay. So, now if I fix the value of x at k, I got k heads, right. So, if n is below k, this whole thing will go to 0. Okay. So, you have to be careful here. So, this n equals k to infinity is a big step here. So, if n is less than k, this guy becomes 0 if n is less than k, isn't it? So, there is no way you can get k heads if you only tossed less than k times. Okay. So, it is non-zero only if n is greater than k, isn't it? K goes only from 0 to n has to be greater than or equal to k. So, you start from k to infinity and do this summation, you will get a distribution for x. Is that okay? So, hopefully, I do not know, I mean, I will leave this as it is. If you have the energy and enthusiasm, you can think about how you will add it up and what you will get at the end. Okay. So, maybe I should try it, I do not know. Let us see if we get somewhere. Okay. So, this n factorial, this n choose k, I am writing n choose k in this fashion. So, notice this notation here. So, let me write it down. You may have been used to this notation. Both of these are commonly used. Okay. So, these two are the same. Okay. So, nck and this putting long bracket with nk in the middle, that is also nck. Okay. So, get used to that. I will use this n choose k a lot. Okay. So, you can try to simplify this. I am not sure if that is the main point of the score, but anyway, so you can try to simplify this. How will you do it? So, you know, n choose k is n factorial by k factorial times n minus k factorial, isn't it? You can do this, right? And I mean, so after this it's just manipulation, but let me just do this, it's not too difficult. So you have this summation n equals k to infinity e power minus lambda, right, and then you will have lambda power n, and this n factorial and this n factorial will cancel, and you will have a k factorial times n minus k factorial times half power n. Okay. So I am going to do something here. You may or may not recognize this trick. It's a little trick that I am doing to get something something out of this. Okay. So let's see here. So I am going to write this like this. Okay. So I am going to pull this e power minus lambda out. It does not depend on n. I am going to pull the k factorial out, and I am going to pull lambda power k out. Okay. So why am I doing this? Because then I will get a familiar form, and then I can use it. Okay. And then even for this half, I am going to do the 2 power k out and write this as n equals k to infinity lambda power n minus k by n minus k factorial times 2 power n minus k. Okay, so you can see what I have done here. I have pulled all the k part out and kept only the n minus k inside the summation. I am summing from n equals k to infinity. You can try writing it out differently. You will see this is exactly what you will get. And this summation, okay, this summation, right, if you look at it very carefully, you will see this summation is e power lambda by 2. Okay. So, I mean, there are various ways to identify this. So, you know, this part you can replace with lambda by 2 power n minus k, and you are going from n equals k to infinity lambda by 2 power n minus k by n minus k factorial. Okay. That is exactly, you know, e power lambda by 2. Okay. So, once you identify that, you can come back in here. It's e power lambda by 2, you have e power minus lambda plus lambda by 2, that will give you e power minus lambda by 2. So, you see that this fx of k becomes this very interesting little expression e power minus lambda by 2 times lambda by 2 power k by k factorial, isn't it? Isn't that interesting? So, notice what happened here. Okay. So, x had got this distribution. This is a very interesting distribution property for Poisson. So, notice what all is involved here. I mean, it seems like a lot of work with algebra and manipulation, but that is what it is, and you get a very nice result at the end. I will tell you why this result is very interesting. Okay. So, you fix any k and try to find fx of k by marginalization, and this marginalization is not as easy as the previous marginals we computed, because in this case there is an infinite summation involved, and you have to use all sorts of trickery to manipulate the expression, move this around. Even if you did not follow every step that I did, take your time, work your way through, you will understand that it is all okay, and you will finally get this very nice expression, and this is for any k, right. So, k could go 0, 1, 2, so on. Okay. So, what have we identified here? What is this distribution? This implies x by itself is actually Poisson lambda by 2. Okay. So, look at that. Isn't that interesting? Okay. So, you started with a Poisson distribution n with parameter lambda, with that you know, the parameter of the Poisson being lambda, and then you did this little experiment where you first took the Poisson random variable, took some value from it, and tossed a coin as many times as that Poisson random variable was. If the Poisson random variable was 100, you tossed the coin 100 times. If it was 10, you tossed the coin 10 times. And then in the number of tosses that you did, how many heads you got became your random variable x. Okay. And notice what has happened. This x itself is another Poisson random variable, and it's got parameter lambda by 2. And where did that by 2 come from? Where did the 1 by 2 come from? It's actually probability of success in your toss, right? It's the coin toss being half, right? That fair coin giving you a probability half for the heads. That's where the half came from. And look at how we did the work. It just went through the basic definitions, but maybe this manipulation is a bit messy. Maybe you need one more sheet in which you want to write it down. I'll leave that as an exercise. But this is an interesting little property we got from the Poisson distribution, and this is quite useful. Quite often in a lot of calculations, this is used with Poisson random variables. This makes Poisson random variables very simple in practice. Okay. Hopefully you understood the steps of this problem, but the final result is more important than the way we simplify it. You do a Poisson, first sample a Poisson, get a Poisson random variable and do something that many times, and if your success event was had a probability, the number of successes becomes Poisson random variable again. Okay, so it's an interesting property of the Poisson distribution. Okay, all right, we can generalize this a little bit on all, but we'll see that later. Okay, so let's come back to a much more simple finite example. Okay, so we saw that Poisson random variable, anytime things go to infinity, it's a bit scary, isn't it? I mean, it's okay, you'll get used to it if you work with it for a while. Let's come back to a finite example, simple examples where you can write down tables and feel happy about it. Okay, so let's look at that. So x is the number of, so we come back to our familiar IPL power play over. I've been talking about distributions around the IPL power play over a lot, and we'll continue that in this course. Once again, I'm at the IPL power play over, and I'm going to let a random variable x denote the number of runs in the over, and y is the number of wickets in the over. Okay, number of people who got out. All right. So let's say the marginal of y is known. We're going to assume some very typical marginal. Most of the time there's no wicket, that's 13 by 16, and then there's one wicket with probability 1 by 8 and two wickets with probability 1 by 16. That's the marginal distribution of y. Okay. And then what's given is the conditional distribution of x given y takes a particular value. Okay, and I've sort of used the intuition here. So if there were no wickets in the power play over, maybe the runs are slightly higher, and if there was one wicket, maybe the runs are slightly lower, and then if there are two wickets, maybe the runs are really low. Okay, so this is a good thing to sort of visualize. Maybe here the table again is something you can write, maybe, but it's a bit more laborious to write down a big 3 by 12 table. One could do it. It's not very hard, but maybe one can also write down something much more interestingly. Okay, so let's see what we can do here. Okay, so the conditionals are given, and you can write down the joint distribution, isn't it? Any t comma t prime is something I've been using for the joint distribution. Simply it's fy of t prime times fx given y equals t prime of t. Okay, so notice I can also I can do any product. Like I can write marginal of x times marginal of y given conditional of y given x equals something. You can also do the other way around, right? A and b is b and a, both of them are exactly the same, so I can do it either way I like. So a typical calculation, supposing you want to do fxy of let's say 1 comma 6. Okay, I'm going to get fy of fxy of 6 comma 1, sorry, fy of 1, which is 1 by 8 times in the conditional distribution of x given y equals 1, what's the probability of 6? Remember, this is uniform, so it will just be 1 by 7. Okay, so you will get some number here. On the other hand, if you were to do fxy of let's say 8 comma 2, okay, so I'm going to get 1 by 8 times 0. Okay, so this will become 0. Okay, so you will get different numbers of this sort. Okay, so if you want to say find fx of t, okay, how will you do this? You have to marginalize, isn't it? So t could take values from 0 all the way up to 12, isn't it? The values that x takes starts from 0 and goes all the way up to 12. Okay, and so one way to represent fx is to draw some graph like this, put t here and put fx of t here. Okay, so this is a very common way to represent a PMF, right? So you draw something like this. So you can put t equals 0, and then you have 1, so 2, maybe this is not a very nice way of writing this down, so sorry about that. So let's just do this. Oops, let's go a long line. Okay, there you go. T 0, 1, 2, right? And then 3 and 4 and 5 and 6 and 7 and 8 and 9, 10, 11, 12. Okay, so those are all the values that t can take. Now, what's the probability that fx t equals 0? Okay, so if t is going to be 0, I have to sort of marginalize over y. Okay, so if you look at fx of 0, okay, this is just if you want to sum over all y, only when y is 2, x is 0, right? Otherwise, x is not even 0. So, this is the same as fxy of 0 comma 2. Okay, and for that you will get a probability 1 by 16 times this is 1 by 7, isn't it? The conditional probability is 1 by 7. Now, what about fx of 1? You will also get the same number for fx of 1. Okay, 1 also happens only a single time, and that's how it is. So, this 1 by 16 times 1 by 7 is one value here. So, this is fx of 0, and that's the same thing as fx of 1, and that common height is 1 by 16 times 1 by 7. Okay, all right. Now, what about 2 onwards? Now, 2, 3, 4 happen here. Okay, actually 2, 3, 4, 5. 2, 3, 4, 5 happen here as well as here, isn't it? So, if you are doing fx of 2, that is going to be, so maybe I should write it here, otherwise it become a bit more messy. So, if you are doing fx of 2, it is going to be fxy of 2 comma 2 plus fxy of 2 comma 1, right. So, you see the marginalization happening. So, you see how I am marginalizing, think about it. So, x equals 2 occurs when y is 2 and when y is 1. Y is 0, x equals 2 will not occur. So, I do not have to worry about it. So, I am keeping x fixed at 2 and summing over all possible values of the other variable. That is the rule. Marginalization rule is you keep your value you want fixed, sum over the values taken by the other random variable, whatever is possible. If that is not possible, then joint PMF is 0, you do not have to add. Okay, so there is no problem there. So, you do this. So, what is each of these values? The first one is 1 by 16 times 1 by 7. The second one is actually y equals 1, right. So, that is 1 by 8 times 1 by 7, okay, isn't it? So, you have here 1 by 16 times 1 by 7, 1 by 8 times 1 by 7. Here you have 1 by 8 times 1 by 7. If you add these two, you will get something. I do not know what you will get. 3 by 16 times 1 by 7. And where will that go? That will go a little bit higher. This is 1 by 16. So, it is probably going to be 3 times that height. So, let us put that guy here. 2, 3, 4, 5 will be at that height. Okay. And what is this height? That height is this guy. This kind of a plot is called a stem plot or something, and it is very useful to sort of picture a PMF. If you want to picture a PMF on the axis, you can draw the PMF as a plot like this, and sometimes a plot is useful for you to see as opposed to writing just a equation, isn't it? So, that is useful. So, after this things get a little bit interesting. 6 for instance shows up here. Maybe I should do a multicolor presentation. Let us go to blue, this blue. 6 shows up here, here and here. Okay. So, if you are going to write fx of 6, you will have 3 terms, fxy of 6 comma 2 plus fxy of 6 comma, okay, so maybe I should write it somewhere else. I don't know where. Below here. Let me write here. Okay, fx of 6 is fxy of 6 comma 2 plus fxy of 6 comma 1 plus fxy of 6 comma 0. Okay. So, this guy is 1 by 16 times 1 by 7, this guy is 1 by 8 times 1 by 7, this one is 13 by 16 times 1 by 7, isn't it? So, you will end up getting, you know, all 3 of them adding up, and you will just get 1 by 7. Okay. So, notice how much higher it will be. So, let me just draw this for you. So, if it's like, you know, this is 1 by 16 times 1 by 7, this was 3 by 16 times 1 by 7, this is going to be just 1 by 7, right. So, it's going to be like 16 times this guy So, it will go really high, so maybe it will go up to here, okay. So, that is 1 by 7 for you, okay. So, now let us come back to 7 and 8. So, maybe I will use a different color here. 7 and 8 are here and here, okay. So, that will go as, you know, if you were to do fx of 7 or 8, you will get 13 by 16 times 1 by 7 plus 2 by 16 times 1 by 7, that is 15 by 16 times 1 by 7, isn't it? Okay. So, that is like, you know, a lot of height here. So, let us go here and here. Oops. Okay. So, that height would come here. Okay. And then you have 9, 10, 11, 12, and 9, 10, 11, 12. If I have to pick one more color, what are the various colors out here? Let us see this one, orangish, yellowish color. Okay. So, 9, 10, 11, 12 is going to be just, you know, 13 by 16 times 1 by 7, a little bit somewhere here maybe, right. So, there you go, that is your PMF, right. So, this is, let us say 13 by 16 times 1 by 7. So, notice how I looked at different ranges of numbers very carefully depending on the conditionals, right, and got different values for the marginal distribution of x, okay, number of runs in the over. So, notice how the modeling went. You first found the marginal of y, or you were given the marginal of y, and then you were given the conditional of x given the particular value taken by y, and then you had to add over all the possible values of the joint PMF to get the distribution of x, and we got this interesting little distribution, okay. So, we saw 3 examples of how in a problem or a given situation or a scenario, you have to work with the marginals and the conditionals to go to the joint, and then maybe even go to the other marginal, right. So, you are given one marginal, one conditional. So, you go to the joint, and from there you go to the other marginal, okay. So, this kind of a loop you can do, so that, you know, given some partial information about the distribution, you can complete it out and find the entire distribution, okay. So, in most real life scenarios, the real trick is to come up with these distributions, right. So, how do you come up with these conditionals, right? In the IPL power play over, I just came up with some random model for the conditional PMF. Why is that conditional PMF ever true, right? That is the non-trivial sort of non-mathematical problem in this area. Once you give me the distribution, doing all these calculations is a very definite and easy thing to do, but you should be very skillful in these kind of computations. This kind of computation should be very clear in your mind, and that is sometimes useful to do other things as well. Okay, so those were 3 examples. We will go on to the next topic in the next lecture. Thank you.